Hello and welcome to this presentation on resolution and its relationship to the number of averages you choose. Spectral resolution is very important. The resolution gives you the clarity to see sidebands, to distinguish different peaks from each other and so on. For example, if you've got a two-pole motor, the 2x vibration peak will be close to the twice line frequency peak, and you can confuse misalignment with electrical faults in your motor as a result. Same way with a 4-pole motor, the 4x peak is going to be close to the twice line frequency vibration. Pole pass sidebands, gear mesh sidebands, hunting tooth frequency sidebands, bearing tone sidebands and harmonics. There are lots of reasons to have higher resolution measurements. Now, a long time ago, the issue with resolution was either the instrument capability or memory. Higher resolution measurement, when we go from 800 lines to 1600 lines to 3200 lines in a spectrum, it takes more memory. But I hope that most of you now have analyzers with a lot more memory, so that shouldn't be an issue. But what most people realize is that by increasing the resolution, the measurements take longer. And that's the point I want to address here. Firstly, just to drive home the point, resolution is important. It enables us to see peaks, little sidebands in this case, where before we could see none. And there are a lot of examples. The trouble is there is a trade-off. The higher the resolution, the greater the amount of time that that it takes the analyzer to acquire the data, and therefore the longer you will be at the machine. If you've got a lot of machines to test, and if some of those tests are, machine tests are in a hot environment, that might be something you're trying to limit. If we look at this table here, it's a bit complicated, but you can see that as I increase the number of lines of resolution, keeping the F max constant, we get better and better resolution. We can separate the peaks more clearly, but we increase the number of time it requires for each average. So if you've got 4 averages or 8 averages or 10 averages, you have to increase this number. But basically, as we increase the number of lines of resolution, we are improving the resolution. The data collector internally is capturing longer time waveforms in order to calculate the spectrum. So your time waveform, depending on how you've selected it and other things, the time waveform you collect is probably going to have more data in it, but it's going to take longer. So it is a compromise. You increase the resolution, it increases the time taken to acquire the data. Remember that the whole point of testing the machine is to get all of the detail from the machine so that we know, if there is a fault and what the fault is. And imagine that the machine is trying to tell you what's wrong with it. At the same time as it's telling you what's wrong with it, there's also noise from outside the machine, there's noise from inside the machine. So we've got to deal with the noise. But as the shaft turns, as the gears mesh, as fluid goes through the pump and maybe it cavitates, and as the balls roll around in the bearing, the vibration from one moment to the next changes. Now, using a higher resolution gives us more clarity into what's going on. But we do need to listen to the machine long enough to get repeatable measurements and to hear everything the machine has to say. However, if you've watched any of the quick presentations on averaging, I said all the same things. And that's why we're going to relate resolution to the number of averages. Let's have a look at that for a minute. When I look at my data here and I choose 800 lines of resolution and I ask the software to do an average with 50% overlap, okay, a few settings there, but what happens is it's going to grab a chunk, do an FFT of that and show it to me. Then it's going to grab another one from this chunk of time, do an FFT, window it, do a window FFT, and average it. And again, and again, and again, and again. So let's say we took 6 averages. It has taken until this time, see where that orange line is? We've decided that 6 averages is the right amount of time for this machine. The averages are now stable, we've got a good repeatable measurement. Now, I'm going to increase the resolution to 1600 lines. Notice that as I switch between 800 to 1600, the box is now bigger. That means it is using more of that time waveform to give us the spectrum with more resolution. In case you're interested, the sample rate has not changed. That's based on your Fmax setting. So all it's doing is it's listening for longer and it gets a higher resolution measurement. And everyone might say, well, if you go through those 6 averages, 1 average, 2, 3, 4, 5, 6, oh dear, we're now sitting out here for almost twice as long. It's overlap averaging, it's not going to be twice, but it's almost twice as long. But wait a minute. Didn't we originally agree that this much time from the machine was enough to hear its story? So if I go back and say, well, where was that line? I shouldn't have hit reset, it was about there, I think. If I go 1600 lines and go 1 average, 2 average, 3 average, well, we've now heard from the machine everything the machine has to say. We've used overlap to take care of the windowing issue. We now have repeatable data. We've not stayed at the machine any longer than we did before, but we've got high resolution spectra, and we've got a time waveform that is longer. Because the way the FFT calculation works, there's kind of an averaging process going on. You know, as it iteratively goes through this time waveform and comes up with the FFT, that's the process that's going on. The bottom line is you can increase your resolution and lower your number of averages. You'll still get good data from your machine in terms of repeatability and dealing with the noise, but you'll now have a better spectrum and a better time waveform. Bonus. Good deal. I hope that presentation was useful to you. Thanks very much for viewing it.